This is an example of a coil spring in action under load that supports the rear suspension of an off-road vehicle. When you design a coil spring for such a system, you want to make sure that it can handle the expected dynamic loads, that the spring coils do not bottom out, that they do not plastically deform, and that they last as long as you want them to last. In our first few lectures on springs, we understood how we were going to express the stress in the spring and how we would relate the load and the deflection through an elastic spring constant. This image shows two types of helical coil springs which are designed to be loaded in compression. On the left side, we see the top view of this helical compression spring and a side view of that compression spring. In this particular case, we have done nothing with the ends of the spring. They are not turned and they are not ground. And so this particular spring, if you tried to stand it up and load it in compression, it would fall over if you didn't support it. We can take that simple plain spring and we can grind the ends of the last coil and we end up with the spring shown on the right. And in this particular case, once we have ground the end coil, this spring, when stood up on its base, would stand freely. We then load the spring with a force F, and we want to find a relationship between the force and the displacement. So we know that this spring is going to be elastic to some point, and so its force will be related through an elastic spring constant to the displacement under the load in the direction of the load. As we load that spring, we also understood that the coils in the body of the spring away from the ends are a combination of direct shear, that's the F over A term, and torsional shear, the TR over J term. Now, there are a number of things that we would like to know about these springs because when we load this spring up, we start with some initial length, which we're going to call L0. And as we apply this load F to the spring, centers of adjacent coils will approach each other. Now, it turns out that when you first wind the spring, the centers of these coils have a distance which is referred to by the small letter P, that is the pitch of the coils. How far do you move up the spring for one 360-degree rotation along the spring coils? As we apply this load F, these coils begin to collapse and eventually they are all touching. And so we would get a solid length from that, L sub S, and that solid length in this case, well, you got to look at it and try to figure out what you think it should be. In this case, we have 7 full coils and a half coil down at the bottom and a half coil at the top. So it means that the total number of coils, NT, is going to be equal to 8. And the number of N coils, if NT is equal to 8, the N coils are the half at the bottom plus the half at the top. That's equal to 1. The number of active coils are going to be equal to 8 minus 1, or 7. Where does this number of active coils come from? Well, remember, when we were using Castigliano's theorem to evaluate the spring constant K, we were using elastic strain energy and differentiating that energy with respect to the applied force F, right up here, and that would give us a displacement. And so we can take the known applied force F, divide by the displacement that we get using Castigliano's theorem, and solve for the elastic spring constant. But in order to make that solution tractable, you are going to simply assume the same amount of strain energy in all of the coils, but we know it's going to be different at the end coils. And so this simple approach was taken in the days before computer simulation, where the number of active coils would be equal to the total number of coils minus the end coils, and then you just use the number of active coils, in this case 7, to do the Castigliano's theorem calculation of the elastic spring stiffness. Now, the other thing that's important is this solid length. So if we apply a load and all of the coils touch, that solid length should be equal to the wire diameter, which is given by lowercase d, times what? The total number of coils, NT. So that would be 8 times D in this case. We don't yet know what the wire diameter is because we didn't choose a spring. Now, another important parameter that we introduced, and you got to remember, is the spring index C, which is equal to capital D divided by lowercase d. And capital D is simply the coil diameter, while lowercase d is, of course, the wire diameter. So the spring index is an important thing. The spring stiffness that we figured out previously is estimated using Castigliano's theorem to be the fourth power of the wire diameter multiplied by the shear modulus divided by 8 times the coil diameter cubed times the number of active coils. So it's very important that we put this N sub A in there. And in a previous lecture, I showed you that you are not going to always get really good agreement between the Castigliano's estimate and an actual measured value, either through direct spring compression or a finite element value measured using finite element analysis. So this K is important because we're going to choose a spring stiffness to give us a load displacement relationship that is suitable for the mechanical application that we're going to be using. And then, of course, under the influence of the maximum design load, that F, we want to figure out what the shear stress is going to be in the wires. And we showed that using some simple calculations, if we combine both the direct and the torsional shear, we would be looking at the maximum shear stress occurring along the inner surface of the coils. And we approximate that stress using the applied load F, the coil diameter capital D, 8 times that in the numerator, divided by pi wire diameter to the third power, and we correct for both the curvature and the spring index using the Bergstrasser factor right here, which is 4C plus 2 over the quantity 4C minus 3. And if we're going to be using this spring, we're going to be choosing a shear stress that is less than the yield strength of the material. And we will get to that in a short bit. There are a great many types of compression springs that are used, and this is an example from the Shigley design book, figure 10.2, which shows some of those typical coil springs. The first one in the upper left is the plain end right-hand turning coil spring, and you'll notice that there's nothing special, we just have a helical coil. Then we could take the end coil of that spring right here as we bend it so that it just touches the coil immediately below it. Now that offers a plane that is perpendicular to the longitudinal axis of the coil, and that would probably stand up on its own. This is called squaring when you turn the coil so that the last one touches the next coil. The other thing that we can do is we can square that last coil and then we can grind it flat to create a really nice squared and ground end coil spring, which will really happily stand on its own. Or we can take this simple plain end right hand and we can, instead of turning it, just grind it flat. There is a table in the Shigley book that allows you to relate total number of coils, N sub T, which we just talked about counting. We can calculate the number of N coils if we know the free length or the pitch and the wire diameter. We can calculate the free length. We can calculate the solid length rather easily if we know the total number of coils. And the pitch, as I mentioned before, is the distance you travel along the spring for one 360-degree rotation around the longitudinal axis that represents the center of the spring. We use these relationships in Table 10.1 to help us answer questions about the number of N coils, the total number of coils, the free length, the solid length, and the pitch. When we are designing a coil spring for compressive loading, there are a number of conditions that are pretty obvious. First is it must fit in the mechanism. You don't have any wild choices here. You got to make sure it fits. It has to have the appropriate K value so it provides the force deflection relationship that your mechanism needs in order to function. You have to make sure it doesn't close to the solid length, because if it closes to the solid length, your stiffness goes through the roof. During that loading operation, it must not yield. You want to stay away from the shear yield strength. It also must not fatigue, and you want to avoid buckling of that coil spring. We'll get into more of this as we go through some examples.